All right, I'm going to go over the energy review package with you guys. First question is a bit of a tricky one. To start off with, we've got this block being pulled up a ramp by a motor. It's not moving at the bottom, it is moving at the top, and it's up. But it'd be sure nice to know how much work the motor did. Fortunately, we got a force distance graph going over that. And anytime the y variable times the x variable is something useful, the area under the graph is that thing. So in this case, work is force times distance. So it's going to equal the area under a force distance graph. To find the area, I'm just going to find the average force and then multiply it by the distance. Number midway between 50 and 65 is 57.5. If I want to find the average of any two numbers, I can add them up and divide by 2. In this case, I can just figure it out. And so in area of the rectangle, if I take this little section here and put it there, is just 57.5 times 10. So work is 57.5 times 10, force times distance, to get the area under the graph here. And that is 575 joules. For the next part, though, we've got a conservation of energy situation. So there's 150 joules of heat energy produced. I'm going to do it right here. So I'm just going to say 150 joules of heat. So this is really a before equals after. All the energy, like there's no energy before, it all came from work. All came from that 575. So before we've got the work, and then afterwards it's up. It is fast. And it is hot. So work has become potential, kinetic, and thermal. Work is 575. EP is mgh. So I just say it's 10 kilograms times 9.8 times the height, which is 4 meters. mgh. Plus 1/2 times 10 times v squared, plus our thermal energy, which is 150 joules. 9.8 times 4 is just 39.2. 39.2 times 10 is 392. 392 plus 150 is 542, I believe, leaving us with a grand total of 33 joules. Yeah, sounds about right. Equals 5v squared, I think. Maybe I should actually use a calculator. That might be smart. So we have 575 minus 150 minus 392. Yeah, it's 33. And then if we divide that by 5, we would get 6.6. And then take the square root of that. And it should be 2.56, I believe. You can always check the answer key. Keep me honest. That's about it. Next guy. We got this guy. We got a block. Initially at rest, pulled 13 meters across the floor by a 50 Newton force. So it looks like the guy doing the pulling is doing positive work. Here we got a force, here we got a distance. Work equals force times distance, which is equal to 50 times 13, which is 650 joules. Now this is positive work because the force and the displacement are in the same direction. It's pulled right and moving right. Friction is going to be doing negative work. It's going to be taking energy away from it, and also its forces backwards while it moves forwards. Both tell you that it's going to be negative work. So we may as well take that away from here. So our kind of net work, our net positive work is equal to our positive work minus our negative work, which is 380, which I believe is 270. And we want to know the block's final velocity. Well, all our net positive work, after we take away the friction bit, is going to kinetic energy. Work is change in energy, which in this case is 1/2 mv squared. 270 divided by 5, because 1/2 10 is 5, is 54, and that equals v squared. 54 square root is equal to 7.3. So work equals change in energy. Friction's almost certainly doing negative work unless you've got some sort of conveyor belt system, or maybe like a car. Really use friction to accelerate yourself forward or make your car go forward. So technically not always true, but it'll be positive work if it's increasing the object's energy, negative work if it's decreasing it. Yeah, that's the easiest way to think. One excellent power formula that's often overlooked for the next question is power is equal to force times velocity. If you're pushing a crate across a smooth is like physics question code for basically frictionless. So if the crate's accelerating, it means it's getting faster and faster, and it's got a constant pushing force. So if this is staying the same and this is increasing, take a constant and multiply it by an increasing number, you're going to get something increasing. So the answer is A. Next sucker. We've got this ball projected vertically with initial speed of 280 meters per second. So we got kind of a before equals after. Looks like you've got some sort of like cannon on the ground shooting this ball up in the air. It's initially 280 meters per second, and then later when it's reached its max height, it's hot and it's up high, and we want to know how high it is. So before, it's got kinetic. It's got 1/2 45 times 280 squared joules of energy, and all that energy, some of it became the 8.5 times 10 to the 5 joules of thermal energy. So afterwards, a bunch of this energy became heat, plus a bunch of it became potential energy, which is 45 times 9.8 times the height. At this point, it is just math. I'm going to use my trusty calculator. 0.5 times 45 times 280 squared minus 8.5 times 10 to the 5. And then take the answer and then divide it by 45 and divide it by 9.8. And 2073 really. H equals 2,073. So over 2 kilometers in the air. So this is Canon not messing around. Next guy, we've got these graphs. This one's kind of a tricky one. Now, if you think about it, if you drop something off a cliff or whatever, it's getting 9.8 meters per second faster every second. So it's getting this much faster every second. And so after 1 second, it's going 9.8. After 2, it's 19.6. After 3, it's 29.4, and so on. So your time axis is really just scaled by 9.8 to be velocity. So this may as well be velocity. And EK is basically like 1/2 m, so like constancy stuff times v squared. So you know the whole like y equals x squared graph, which theoretically should look like this. It's a parabola. You've seen it before. This is basically that, kind of like v is your x-axis and y equals v squared times some other junk that we don't care about. It'll still have the same shape if you're multiplying it by some constant. Anyway, so this is our answer. Because time is like just, time is equal to your velocity divided by 9.8. So it's really just a scaled version of velocity. And EK is a scaled version of v squared. Know your graph shapes. They're useful for stuff like this. This I don't know if is a thing. This is just kind of like y equals some negative value times x plus some y-intercept. And this is just y equals x. Next guy, balls drop from a tree and falls to the ground. Which of the following best represents the ball's total energy as it falls? It's losing potential, gaining kinetic, maybe there's some thermal in there, but the total, if it counts all of those types, will always be the same number. Like if you started with 100 joules, later on you might have like 50 potential, 40 kinetic, and 10 thermal, but you add it all up, you're still back to 100 joules. So your total is staying constant. Next guy, we got this guy here. What's going on? We're going to find what happens to the block's final kinetic energy and the amount of heat energy if the coefficient is increased. If the coefficient is increased, there's more friction, and it's over the same distance. Really, like, you should just know this. Like, friction creates heat. If you got a bigger friction coefficient, you're going to have more friction and more heat. And friction is pretty good at slowing things down more. So I think it's relatively obvious that the answer is B. But if it's not, if you want a full-on logical thing, bigger mu is bigger force of friction. Heat is work done by friction. Work of friction, which is equal to force of friction, times distance, which is equal to, in this case, mu mg, because gravity is equal and opposite to normal force, in this case, times d. All of this junk stayed the same. This guy went up. Your thermal energy's gone up. If your thermal energy's gone up, it must come from somewhere, and the only other place is kinetic. Like you've got heat here and you've got kinetic energy. If at the end you've got more heat energy, you must have less kinetic energy. Yeah. Also, it would have done more negative work on the thing and reduced its energy. So that's that idea. Next one, we got this ball launched off a cliff top. I like making my zero level the lower of the starting point and ending point. You could make it here. It'll still be right. You'll just have an extra potential energy term you don't need that you'll get rid of in your first step. And I'm lazy, so I don't want to like waste time here. This is an equally valid zero height, so I'm going to use that. So if this is my zero, before I have no potential energy, and after I have potential and some kinetic. So I'm going to do before equals after. One half times 1.2 times 16 squared is my kinetic energy before, which is all I got before. After I got potential and kinetic, so I've got my MGH. Now the big change here is I'm going to use a height of 4 rather than 19 because I like my zero level there. And then plus my EK, which is what I'm looking for. 16 squared, I think it's 256, divided by 2 is 128. 128 times 1.2 is 153.6. And then I'm just going to subtract off this junk, whatever, however many joules of it became potential. So that would be 1.2 times 9.8 times 4. Which leaves me with a EK of 107. Which in sig figs is that sucker. All right, next guy's a good one. You got an aircraft. It got started on the ground, so no energy. And then later on, it is up in the air, so it's higher and it's faster. And we want to know minimum average power, ignoring all frictional stuff. So we're just going to say, hey, power is equal to change in energy over time, because that makes the most sense given what we know. It got higher and faster, so change in energy makes sense. It can be both, further up in the air and faster. So our change in energy is mgh plus 1/2 mv squared, because both of those energies changed, and time is 920. So what we got? We got big boy aircraft times 9.8 times 9,500 plus 1/2 5,500 times 210 squared all over 920. So whatever that happens to be, I don't actually know. I guess I can find out. So this is what my calculator gave me. Very much not using sig figs. And so our answer is that. Next guy, we got a force distance graph again. Remember, if our y value times our x value is something useful, area under the graph is what we're looking for. And we want to find the area under the graph between here and here. We got kind of this funny sort of shape again, sort of like a rectangle underneath and a triangle. And so again, what I'm going to try and do is just find the average force, because that's effectively like taking this chunk here, shoving it right there. And then I've just got the area of the original shape is the same as the area of this shape, which is just a rectangle, which in this case is just 10 times 0.6. because this is 0.6 and my average force was 10. So 10 times 0.6 is 6, shockingly. And then on to the next guy. We got a very similar question to the 2 before now. Same kind of deal, except it's work this time. So it's just work is change in energy, which in this case, we've got another plane which got higher and faster. So that's just equal to 1,500 times 9.8 times 3,200 plus 1/2 1,500 times 65 squared. And after using my calculator, I get this sucker, which is right here. Not so bad. Another force distance graph. I wonder what I will do. I will find the area underneath. And look, we got another funny, like, kind of thing we can convert into a rectangle by taking this and shoving it there. So average force times time. Our average force is 10. So 10 is the average number between 8 and 12. And the distance I'm exerting the force for is 0.2. 10 times 0.2 is 2. So that's pretty quick. That's all that. We want to know efficiency next. Efficiency is kind of what you output divided by what you input. In this case, his body is the machine. So you'd say like, yeah, I'm a machine. And the input to his machine is this much food energy. So that much in Big Macs or whatever. And what he's accomplishing is increasing his potential energy. So that's just MGH, which in this case would be 75 times 9.8 times how much he went up. If you go from 250 to 490, you've gone up I believe it's 240 meters. So that's what we'll put in there. So that's 0.63 or 63%. Not bad. I don't think warm-blooded creatures tend to be that efficient. So unlikely. More like 25 with fair variance. Change in kinetic energy is equivalent to work. Work is just change in energy. 16 kilogram object dropped from a height of 25 meters and strikes the ground with a speed of 18 meters per second. And we want to know how much heat energy was produced during the fall. Well, it sounds like a before equals after to me. Before you got EP, it's up. After it is moving right before it hit the ground, plus it's hot. Some of the initial potential energy has become thermal through friction. So we'll just do 16 times 9.8 times 25 to get the initial starting potential energy and make that equal to 1/2 16 times 18 squared. And then solve for E thermal. And answer is 1,328. So yeah, with sig figs, we got that guy. Another force distance graph. I wonder what we do. Force times distance, our y variable times our x is something useful, and that's equal to work. So area under the graph must be work. if the y times the x is that. So I'm going to break it into a triangle and a rectangle. So 20 times 10 divided by 2. 20 times 10 over 2. That sounds to me like 100. 100. Anyway, it's 100 there. 100 joules in this first section. And then here we got 20 times 5. Because going from 10 to 15 is 5. 20 times 5 is another 100 joules. So in total, we got 100 joules because of the triangle and 100 joules because of the rectangle. So we have a grand total of 200 joules of work done. And it looks like, based on, it doesn't mention moving up at all, and we're interested in the speed. Work is equal to change in energy, and the type of change in energy here is probably kinetic. So half of 8 is 4. 200 divided by 4 is 50. And the square root of 50 is 7.1. Just over 49. All right. Now here's an evil one. And I'm going to try and explain. So if you look at it just at this point, it has an initial horizontal velocity and a known kind of vertical height it's falling. So if you remember all our like little horizontal projectile motion stuff from earlier in the year, basically the time to fall doesn't depend on how fast this is moving. Like if we change the height, it's going to change the speed, but it won't change the amount of time it's in the air. So our distance is equal to velocity times time, but that time is just staying the same. So at this point, whatever we do to the velocity, we'll also do to the distance it goes. So if we like double the velocity, we'll double the distance. Anyway, time is the same because something launched horizontally will hit the ground at exactly the same rate as something just dropped. So now we just got to figure out how changing our height affects our velocity. And it'll be a little tricky, but bear with me. Here is what I call a let proof. I'm going to say first let's solve for velocity. So we've got potential energy becoming kinetic energy. I'm going to cancel this, move the 1/2 to the other side and take the square root. And I will have V equals the square root of 2GH. Sounds good. I'm going to say let the velocity when I drop it from height h equal this. I'm going to say the velocity when I drop it from a height of 2h, that would be same formula. Everything's the same except now it's going down from 2h. I, for reasons that will become obvious in a sec, I'm going to try and get rid of any difference in the formulas. So I'm going to pull this out of the square root. So that's going to equal to root 2, which is this guy pulled out, times what we had before, times 2GH. So just move this guy out in front, but the square root, it needs a square root over it because it's still square rooted. But I just defined like root 2GH to be how fast it's going if I bring it up a height h. So I have just said that V2h is equal to root 2 times the velocity if I lift it a height h. And that whole root 2 thing has to do with the fact that you double the height, you double the kinetic energy, but kinetic energy doubles if you just increase velocity by a factor of root 2, because it'll get squared into 2. Anyway, So whatever we do to the velocity also happens to the distance. So if we double the height, we root 2 the velocity, multiply it by root 2, and so we will also multiply the distance by root 2. All right. Next guy, we got a machine rated at 1500 watts. This is an input. Anytime you talk about a machine's energy, that's how much, say, electricity you got to put into it to make it work. So efficiency is what you put into it. In this case, I'm going to do power divided by what you get out of it. Oh, crud. Sorry. I did that backwards. That is false. Whatever you get out of it, divided by what you put into it. My bad. Sorry. Power output will be change in energy over time, which would equal mgh over time. And so it will be equal to 100 times 9.8 times 36 divided by 45. So we got 4/5. 4/5 of that is like 80. 80 times 9.8 is like 8 times 9.8 would be 7, 8, 4, I think. So 784 is probably what it is, divided by 1500 watts. So that's a little over half. So it looks to me like this guy. And there we are. Next guy, we want to know minimum work done when our student climbs to a height in a time. Time's not going to factor into this. This is a big troll to make you try to solve for power. But work is change in energy. And if climbing stairs, what you're mainly doing is increasing your potential energy, which would be 65 times 9.8 times 8. And 4, 5. 65 times 9.8 times 8. Yeah, it is 5,100. All right, we've got this Carden Rider start from rest on a 20-meter high incline, and we want to know how much energy is transformed into heat. We're going to have to do conservation of energy to find how much energy is transformed to heat, which shouldn't be too bad. Before, it looks like we just got potential. Afterwards, it looks like we got kinetic and thermal. So just before equals aftering it. So we got EP equals EK plus E thermal. So we've got 170 times 9.8 times 20 equals 1/2 times 170 times 16 squared. Plus E thermal. Looks like E thermal is equal to 11560. That is not sig figs. Sig figs should probably be 3. So 1.16 times 10 to the 4. Ideally, but whatever. And we want to know the average force of friction. Now, E thermal is equal to the work done by friction. So E thermal is equal to the force of friction times distance. So we got our 11560 equals force of friction times 60 is the distance it acted for. 60. So that gives us a force of friction of 193. Alrighty, next guy. So we're trying to figure out how much energy must have momentarily been stored in the trampoline when he came to rest. Again, it's before equals after. There's only so many tricks in this unit. Should be a good one, hopefully. So before, he's got potential energy. I'm going to make this my 0 level, because I like to make the 0 level the lowest of my starting situation or my ending situation. And that'll just work better. So before, I'm saying he's got EP. Afterwards, I'm saying he's got E spring. So really, I'm just looking for MGH because that'll equal the energy stored in the trampoline at this instant. So it's just 55 times 9.8 times 9. So that's how much lower he is. Which is 4,851. Bam. Done. How much work must be done to stop a 1,800 kilogram vehicle traveling at 30 meters per second? I don't know, but work is change in energy. Now it looks like the type of energy change in here is kinetic. So I'm just going to do 1/2 1800 times 30 squared. 30 squared is 900. Half of 1800 is 900. 900 times 900 would be 801,000, which is this sucker. Alrighty. Next guy, we got this roller coaster situation. We've got another before equals after, shockingly. And before, it looks like we got EK plus EP because it is up and moving. And after, we've got EK because it's moving and it created some thermal through friction. So we just plug her in. 1/2 times 250 times 4.5 squared, because that's how fast it's moving initially, plus 250 times 9.8 times 18 gives us our potential energy in the beginning. So that's our total before. And that's got to equal 1/2 250 times 15 plus the thermal. So and that gives you an E thermal of 18,506, I believe. Yeah, it should be about right. That's in joules. Work is also measured in joules. Energy is joules, and work is just change in energy. And I'll save the rest of it for another day. Thanks for listening. Hopefully you find this helpful.